Welcome back, guys. Before we start polar, we're just gonna recap the director circle of a circle, because we're gonna explain the director circle of an ellipse. Remember, for a parabola, there is no director circle. We found out that because it's an open shape, and if you go to the previous, or I believe it was lesson number 7 or 8 in this lengthy introduction, that because it flattens out and it opens up at the end, the directrix, the locus of the set of points, the collection of this, or the set of points of all the perpendicular tangents they're gonna meet here at the directrix, not the director circle. That's for a parabola. For a circle, it was a lot easier. Look at it. Two tangents, perpendicular. No matter how you move them, they're gonna be what? They're gonna be, equidistant from that center. Look at that, because we make a square here, remember? So this is gonna be, the new radius will be r equals square root of 2 times the original radius. Okay? Now there's one more thing that we didn't talk about that we need to talk about here so we can understand what we're going to do with the ellipse. We talked about how the new radius is forming this new director circle, which is also a concentric circle, because now we have a new r here with the same center and a new radius equaling square root of 2 times the original r, right? But look at the point of tangency, meaning this point. The point of tangency, even if you keep moving it around, point of tangency here, point of tangency here, the point of tangency of any tangent around this original circle is also what? Is also equidistant from that center. It's always equidistant. However, and this is where we're going to start with the ellipse. However, the point of tangency, you can tell me, okay, I understand, they're perpendicular, okay? And then the distance here is going to be the squish distance b. It's not the same radius. And here it's a, but I'm not talking about that. I am talking if you move them, look at that. If you move these two perpendicular tangents, they become in that, right here, they meet right here. The point of tangency now is here. Now and the other point of tangency is here. So this distance is always changing. So we need to figure out how is that distance changing in regards to all these elements that are or features of an ellipse. The a, the small b, the small c even. This c maybe, we will find out. And right here, any tangent has the equation of what? Y equal mx plus b, or mx plus c, or mx plus d. We're going to keep it c because we don't want to confuse it with this b, okay? Let's put it at c. And if we find out that we need to use a small foci c, then we will move it to d. But we're gonna keep it at c. We're not gonna need that c. We're only gonna need the a and the b. So instead of confusing, and look, even when the y equal mx plus b or mx plus c changes around, look at that. It's not that it's parallel to the r. It's still proportional to that equation where the r is. Everything is proportional here. However, because the point of tangency is not equidistant, it changes here. Nothing is proportional. When I say it's proportional, remember, in the equation of a circle, a equals c, x squared plus y squared equals, or x minus h squared. And everything that derives from that stays proportional with coefficients and ratios. Here, we need to establish this proportionality. Is there anything proportional in order to figure out these tangents and the director circle and the tangents in the next lesson with the parametric, using parametric for an ellipse? What is the difference again? Anyone? You can text me. The difference between parametric and polar in the case of an ellipse. It's the hidden, let me see. Yes, it's the hidden parameter theta, the angle, okay? The angle that is formed, let's say you have a point P here, this is the angle theta, and it goes counterclockwise. And if you have concentric circles and polar, this is between minus pi and plus pi, and you have a lot of representation, unlimited number of representation. However, the same angle theta, if you use it in an x and y setting, it's only between 0 and 2 pi in the first revolution, in the first rotation. But that's not our discussion now. Our discussion is that those points of tangency, when you move those perpendicular tangents around the ellipse, are not equidistant, they change. So the proportionality of two tangents that are perpendicular to an ellipse with regards to this A and B are going to keep changing. So this is what mathematicians started to study a long time ago. Maybe I think it was like around 300-400 years ago. And when they were studying this, they came up with this restriction that we have. They call it restriction. They were studying this proportionality between these tangents y equal mx plus c. They didn't call it b because they don't want to confuse it with a small b. So if we have this ellipse stretched horizontally, okay, and we are not in polar mode, so we have our y-axis and we have our x-axis, okay? And let's take a point P on the ellipse. Let's take it right here. Let's say this is P, okay? And let's say this is Px1, y1, okay? And if you have a tangent here, the tangent is what? Let's call it, instead of y equal mx plus b, mx plus c, this constant, or this y-intercept here, okay? But let's call it c for a constant. So I have this point P, and, all they want to do, they want to find out, will there, because like we said, when we take the tangents, the perpendicular tangents here, the point of tangencies are not, they're not very, and then you move them. Look, the distance from here to here is not the same distance when you take those two perpendicular tangents. This is B now, and this is A. So they wanted to study the change in the proportionalities between the tangents that are perpendicular and going around the ellipse in a director circle that we're going to find out its equation. And is there any restrictions? Is there any features that we didn't pay attention to? And they came up with something, they call it the restriction or the condition that we need in order to draw these perpendicular tangents, or any tangent actually, any tangent to an ellipse, and you will find out with me why, in order to for a line to be a tangent to an equation of that form, x squared divided by a squared plus y squared divided by b squared equals 1, in order for any line to be tangent, let alone after that, perpendicular to intersecting perpendicular tangent, there is a condition that this line has to fulfill, okay? So the point P on the ellipse is x1, y1, okay? Cartesian rectangular. So this point P satisfies what? The equation of the ellipse. So you can write x1, right, squared divided by a squared plus y1 squared divided by b squared equals 1. So far, so good. Now, it's x1 times x, or x1 times, yes, it's two x's basically. So for the sake of deriving this and explaining it to you, we're gonna keep one of the x1 as x1, and the other one we're just gonna keep it as x, okay? And that's all I did. A squared plus, you know, y times y1 divided by b squared, okay, equals 1. That's, you know, nothing magic or fancy here. And all I'm gonna do is just, you know, put the same denominator. So basically, I'm gonna put denominator a squared b squared, okay? So on this side, I'm gonna do b squared x1 times x plus a squared y1 times 1, the whole thing divided by a squared b squared equals 1, right? So if you move it to the other side, it becomes like this. So far, so good? That's all I did. Now I see the y here. Because there is proportionality, I want to move this y and isolate it by itself. The same way I write y equal mx plus b for any tangent. I'm going to move this y by itself. So I'm going to put this here. A squared y1 y. This is my y right here. Okay. Equals what? Equals minus b squared x1 x plus a squared b squared. Okay. So now I have it in the form, it's very similar to what? Y equal mx plus c being the constant. Okay, that's all I'm doing. I just put the y, I isolated the y, and it is proportional. It has to be proportional. We're going from, it has to be proportional to the other one because it's fulfilling, it's on the ellipse and it's fulfilling the equation of the ellipse, but it's also fulfilling the equation of the tangent. So it has to be proportional to the other one. So when the coefficients are proportional, that means they are proportional because of the equal ratios between the two. Between the two what, you tell me? Between the two equations that we found. The first one being this, y equal mx plus c, constant. And the second one being a squared y1 y equals what? Minus b squared x1 x plus a squared b squared. So the coefficients are gonna be, the coefficients meaning a squared y squared and 1 minus b squared x1 and m, they are going to be proportional because the ratios are proportional. The p fulfills the two equations here. And I wrote the second one, the ellipse one, as a line one. I'm just trying to use it this way so I can figure out, is there any restriction? Is there any relation between all those A's and B's and C's in order for me to draw a tangent, any tangent to an ellipse? That's all, okay? So if you keep going with those coefficients, what do? You get like this. See, this goes with this goes with this, and this one goes with this. That's all I'm doing. So I can write a squared y1 big Y divided by the big Y here, this Y, okay? Equals what? Equals minus b squared x1, the big X, divided by what? M and the big X. That's all, you know, so far so good, very easy, right? So now what do I have? Now I have something like this. If I eliminate, look here, if you eliminate this, right? What do you end up with? You end up with a squared y1, a squared y1 equals minus b squared x1. y1 and x1 are the coordinate of that point, P, equal m. Now, what do? We take the second here, these two. We're going to take minus b squared x1 x divided by mx is going to equal to a squared b squared divided by c. Exactly. Okay, that's all we're going to do, the number 2 and number 3. So coefficients with ratios, equal ratios, because it's the same equation, fulfilling the same point, satisfying the same point P, divided by mx is gonna equal what? A squared, B squared, and C. But we just found out, you know, that this one also equals what? This one also equals this minus B squared x1 divided by equals A squared y1. So I can also put it as A squared y1. So now, if I come here, I can also eliminate this. And what do I end up with? You can also eliminate this, and then you can get y1 as B squared divided by C. So y1 could be B squared divided by C. So I have a y1 in the form of B squared divided by C. And I have x1 in the form of minus A squared m divided. Now you don't need to memorize any of that. And I'm just showing you how did I get to that condition. Because we're going to use that restriction and that condition to derive the tangents, the equations. There is a special, formula for any tangent to an ellipse and the director circle around this ellipse, okay? So this is y1, the y coordinate of P. This is x1, the x coordinate of P. So I basically wanted to show C, this constant, in my findings, okay? In my x1, y1, in the coordinate of P, I wanted to show this constant that is here, mx plus C. And I did. So all I need to do now, take these findings, instead of x1 and instead of y1, plug them in the ellipse equation and see if I need to make any restriction. So if I plug them here, divided by C squared, and A2, this is, remember, this is x, this whole thing is x1 squared, okay? That's what I found out. And this whole thing is y1 squared divided by b2 equals 1, okay? So if you do, you get minus a squared to the power 2, that becomes a4 m2 divided by c squared a2. So this goes away, this becomes 2, right? And plus what? Plus b4 divided by c2. So, and you still have your, see the C2 here and the C2 here? So equals 1, of course. It's a common denominator, so I can move it to the, yes, Lisa. James, did you understand why? It's a common denominator, so I can move it to the other side. So this is what I have. I have this, James. A4 M2 divided by C squared A2 plus B4 B2 C squared equal 1. This is a common denominator. I'm just going to move it over there. And then this one goes away. This becomes 2. So basically A2 M2 plus B2, because look, this, I only end up with 2, B squared equal C2. And in this situation, this constant in the equation y equal mx plus c, this c becomes what? Because I have it squared here, c squared equal a squared m squared plus b squared, then this c, this constant, you can't call it c, you can call it, but I call it c because it fulfills the word condition also, because it's a c. Condition starts with a c, obviously. So c is going to equal plus or minus radical square root a squared m squared plus b2. This is the condition for any line to be tangent to this equation. What is m? M is your, yes, it's your slope, it's your rise over run. So you need that condition. If the line does not fulfill that condition, the constant doesn't fulfill that condition, you cannot draw a tangent, okay? So let's go back and recap. Let's go to the board now and let's recap what we just did quickly so we can move on to something to get this director circle of an ellipse. Now we know what the restriction is. We know what the condition is. We're gonna go ahead and find out the director circle. So the equation of the tangent equals y equal mx plus c. This constant has a condition. It has to be equal to plus or minus square root of a squared m squared plus b squared. Okay? Now, how do I remember it? Personally, I call it the law of eggs, or the law of breakfast with eggs, or the law of squared morning breakfast, a.m.'s breakfast. In the morning, it's not p.m., it's a.m. And I eat eggs. I love eggs. Many of you might eat eggs or omelets. So it's the squared eggs. It's the law of the squared eggs. That's how I remember it. I don't go, every time I get a problem related to this, I don't do the derivation. I did it for you because we need to do it. We need to understand it, where we got it from, this restriction. But I remember it as the law of morning a.m. squared, or squared eggs. And in the morning, that's why it's related to the ellipse. The ellipse has the oval X shape. So it's a squared, m squared, plus the other squished. I will never, it's all under a radical. It's radicalized. That's how I remember it. And it's a plus or minus, of course, depending on, how the tangent, and where is the tangent in relation to that ellipse. So if I am to plug it here, what do I get? I get y equal mx plus, yes, okay, that's one of them, a squared m squared plus b2, or y equal mx minus a squared m squared plus b2. In some of your books, you see that directly. Some books, they put the condition, they tell you how they derived it. In other books, you don't see it, unfortunately. You just see, oh, those are the equation of the tangents, deal with it. I personally tell you, no, you don't have time to derive this. This is something that, unfortunately, you need to memorize. I made it easy for many students for years now. I memorize it this way. I know how to derive it, but I don't have time to derive it every time. So I had to memorize it myself. It's the law, because it's related to ellipse, oval shape, oblong shape, X shape. It's the law of the morning breakfast, the a.m. breakfast squared. And of course, when you square a.m., a squared, m squared, you need to add that squish, the b squared for the ellipse. Everything is radicalized, is under the radical. That's it. Okay? So now we're going to take these two, and we're going to find the equation of the director of the circle. And we're going to start, let's draw the ellipse here. Keep it here so we don't need to erase it. So if I have an ellipse, where did I put that? Okay, again, I'm not in polar yet. Still here. Easy Cartesian rectangular. Okay? I have an ellipse like this, and let's take them, if you have, okay? So I'm going to find the locus, the collection of all those points that are the intersection of two perpendicular tangents around the ellipse. Okay? I'm going to, of course, this is your A, this is your B. I'm going to call this as a point P or Q or whatever. But I'm not going to make its a coordinate H and K, because I'm going to keep that H and K just in case. In one exercise, we got this not at the zero, shifted X minus H. So we can call them whatever we want. I'm going to call them big E, big G for eggs again. Okay? So big E, big G, just to make it easy, And I'm going to start with that. So I have that condition. This is the condition. Okay? And I plugged it in, if look at this. If you first start with, let's say I want to take this one right here, okay? This tangent. Which condition do you think I should, go with? I can go with, this is a, the slope is rise over run. I can go with this one. I can use the C equal plus square root of that morning breakfast squared plus B squared, okay? So I'm going to start with that. I'm going to see how I can get the equation of the director of the circle, okay? So I'm starting with something like that. Y equal mx plus square root radical a squared m squared plus b2. Now I want to put what? I want to take the mx to the other side. I'll show you why. I want to try to keep the radical by itself on one side and then plug the point. So if I go like this, y minus mx, what do I get? Equals square root of a squared m squared plus b2. Any questions? Yes? Okay. Now, what's the point here? We said the point is E and G. So the coordinate of that point, X is E and Y is G. So instead of Y, I can put G here, big G. Remember the egg? Just to make it, close to my mind. Minus what? Minus ME. This is E. The X is E. I want to square it to get rid of that radical. That's why I moved the radical to the other side. So always, 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 whenever you have a radical, a square root, whether you're deriving or you are, solving something, just square it. This way you get rid of it, okay? So that's it. And now what do? I go g squared plus m squared e squared minus 2mge, right? Agree? All agree? Minus 2mge equals b squared plus a squared m squared. Okay? So I got rid of the radical. Exactly. Now on this side, what can I do? I can write it, yes. See, there's m squared and m squared. Okay? I can discriminant, maybe we need the discriminant, but we might not need the discriminant. We'll see. Okay? So I can write it like this. M squared, okay? I bring this one here, to this side, right? To that side, to the left. So I got m squared, e squared, minus a squared. All agree? Okay. Minus the 2m, g, e, right? What am I left with? Plus g squared minus b squared. G squared, b squared. Right? Of course, equals 0. Okay? Now, if I am to divide everything by what? By e squared m squared. I want to keep that m. Okay? Remember, what's the m? The m is the slope of that tangent, and we are, discussing the collection and the set of points of. So the point could be EG, but it could be also, something else. It could be, another point here with different coordinates. So, I want to keep the m. I don't want to get rid of the m here. Okay, so I want to divide by e squared minus a squared. So if I do that, what do I get? I'm going to erase, keep the bottom one, the one that we just, here, okay? So I want to erase e squared minus a squared. I want to get rid of that. I want to keep the m squared here, okay? So if I divide by e squared, a squared, in the first term, what do I get? M squared minus 2m, right? GE divided by e squared minus a squared. You tell me that's difficult. Not really. You will see where we're going to end up with this. Okay? Now, I also want to divide this constant here plus g squared minus b squared divided by e squared minus a squared. Everyone can see this? Equals 0, of course. Okay? Now, what do I do with this? Look at that. M squared, yes, it is in the form of ax squared plus bx plus c equals 0. But what do we do with this? What's the purpose? Why? We're trying to find the equation of the Directrix circle. And the Directrix circle is related to what? It's related to, yes, absolutely. Oh, it's okay. You can see it on the board. Okay, let's go back to the board then, if you can see it on the board. Okay. So let's keep that. We reached here. Yes, and me do this quickly here. It is in the form of ax squared plus bx plus c, something easy, right? Like if you have something like x squared, James, plus, or let's make it minus, a little more difficult because we have a minus here. Minus 5x, let's say, plus 4 equal 0. What do you do here? Yeah, you do x plus 1, x plus what? 4 equals, or I'm sorry, x minus 1 and x minus 4 equals 0. Why? Because minus 1x minus 4x gives you the minus 5x. And minus 1 times minus 4 equals plus 4. Exactly. And that's what we want to do here. We want to do the m1. Look, m1 times m2 is going to equal to what? Is going to equal to that. What is that here? It's g2 minus b2. So m1 times m2 equals g2 minus b2. What is g? e.g. g is the y coordinate of that point, okay, on the tangent. The point of tangency to the ellipse minus, and that's the x coordinate. Look, I have y coordinate, x coordinate, and I have my a and b so far, so everything looked good. And those two tangents, if you have two tangents, and they're in order for them to be perpendicular, I'm sorry, this is not, the g and the e are not the point of tangency. The g and the e are, the locus, one of the collection of the points. This is here, like this. I apologize, James. Okay, this is your e and g, okay? This is your e and g. What I meant is, now for the two tangent, the product of this AC is this. And in order for them to be perpendicular, this one has M1, this one has M2. What happens? For two lines to be perpendicular, two tangent to be perpendicular, okay, their slopes product is going to equal to minus 1. So this whole thing is going to equal to minus 1. That's it. As simple as that. So g squared of any one of these locus collection of points of the intersection of two tangents minus the b, the squish squared, divided by e, the coordinate of that point squared, minus a is going to equal to minus 1. Now everything becomes very easy. Now we can go back to the tablet because everything now is very easy after this, and I can go ahead and very confidently I can write that I have g squared, that's what we got, minus b2 divided by e squared minus a, small a squared, equals minus 1. So if I do my cross multiplication, I got g squared minus b2 equals minus a, e, big E squared plus small a2. If I move the e squared plus g squared to this side, I get, oh, look at that, a squared plus b squared. What are e and g? The coordinates of this point P, okay? The coordinate of all those locus or set of points that are gonna form the director circle. Here we call them E and G. Here they are different. This is E and G. This is P and Q. You got the idea. And this is a different one. If you get them all, you get the coordinate X and Y of all the points that are gonna make this collection and that they are gonna make this director circle. So instead of E squared plus G squared, all I can do for this circle, I can write X squared plus Y squared for this new director circle equals A squared plus B squared. Okay, and this you know, and in a circle, when you write x squared plus y squared equals, it's usually r squared, right? But your r squared here is what? Is a squared plus b squared. So now the radius of that circle is related to the ellipse, okay? But with a special condition. After we use that condition, c equal plus or minus breakfast am squared plus b squared. We got to that. So now my r equals what? Square root of a square b square. You see that in your book. In some books, they write it right away. They don't explain the condition. They don't link it to the condition, which is a shame, unfortunately, because you're not supposed just to memorize this, you know. Yeah, you can think of it as the breakfast thing in order to, because you don't have time to derive and, you know, think of that all the time. But there is a condition even for that director circle to happen, because it's happening with what? With tangents. And for a line to be a tangent to an ellipse, it has to fulfill this condition, the breakfast condition. C equal plus or minus the radical, it's radicalized, a squared m squared plus b2. Now I can go ahead and put x squared plus y squared equals what? R squared or a squared b2. Okay? That's all there is to this. Now, what else? You know, you're going to tell me, you give me, yes, no. No. You don't, let me go again and show you. So far, we said you need to memorize this one, yes. Okay. The director circle, unless you're studying parametric functions in calculus and the teacher wants you to study director circles, then you need to memorize this. Otherwise, you don't need to memorize it now, and you don't need even to know it, but you need to understand that it's formed with those tangents that are perpendicular and the collection of those intersection of, you know, points where the tangents are perpendicular. And in order for a tangent to be a tangent to an ellipse, it has to fulfill this condition. This is, yes, breakfast. Remember it as the radical breakfast, the squared, am squared, a squared, m squared, plus the squish squared, of course. And then in the beginning, we only did this, remember? And we said we only think of the quantity. If the quantity under x2 is smaller than the quantity under y2, then we put b2, b squared under x2, because this is where it crosses in the horizontal. Yes, and this way the whole ellipse would be in a vertical stretch. And then we said you can also memorize this one if you want to. And so 1, 2, 3, and 4. That's all so far. Okay, that's it. Now, and I will prove to you that it's only these so far. Let's say you got the example of an ellipse. Let's make it like this. 9x squared plus 16y squared equals 144. Okay? And they give you this equation, and they want to know the equation of the director circle. Okay, you know, if you're studying, you know, director circles, parametric functions, polar, if you're in calculus, if you're in advanced, you need to know that at this time it's going to equal what? The equation of the director circle will be, you know, x squared first, x squared plus y squared equal r squared. R squared in this situation is a squared plus b squared. It's what? Where is a and where is b? That's okay. So let's find out where a is and where b is. First, remember the general formula of a conic section. A is not equal to c, so that's good. And a times c is more than 0. The product is positive, so that's an ellipse, I'm pretty sure. And if I divide everything by 144, what do I get? I get x squared divided by 16 plus y squared divided by 9 equals 1. Because 9 times 16 equals 144. Okay? You're usually given this in, with these product of two numbers, and if you multiply them, you will get that number that once you divide with here, you will get to 1 most of the times. Okay. Now, you see that under the x squared, what do you have? You have the big quantity. So this is your a. So you know that a squared is 16. So a is what? A is 4. No memorization. B squared is 9. B is 3. So now I have the a and the b, right? So if I know my a and the b, I just go like this. This is the one of the 4 that you need to memorize. Equals a squared minus c squared. The slack, the element of the slack, remember, a minus c, a squared minus c squared equals the squish squared. So this means c squared is equal what? Equals a squared minus b squared, right? So it equals 16 minus 9 equals what? Equals 7. And then c equals square root of 7. Now, this is stretched horizontally, okay? So, because the big quantity is under the x squared, it crosses under the in the horizontal direction. Now I know that c equals square root of 7, and c equal a times e, right? So e equals c divided by a. So that equals square root of 7 divided by 4, exactly. Now, you could have gotten this in a different way. How? Anyone? Lisa? Yes. Remember we said you start with this and then you write it like this, right? Right? And then you do this. And then now you have what? 1 minus e squared equals b squared divided by a squared. So in this situation, what happens? In this situation, 1 minus e squared equals b squared divided by a squared equals what? What is b squared divided? Yes, b squared divided by a squared is 9 divided by 16, right? So e squared equals what? Equal 1? Yes, exactly. 1, if you take e squared to this side, you have to take 1 minus 9 divided by 16. So that's 16 minus 9, I'm sorry. So that's 7 divided by 16. If e squared equals 7 divided by 16, e equals square root of 7 divided by 4. We just found that out here also, right? See, it's the same, thing. So you don't need to memorize these. See how I told you don't need. Now for the f, for the foci, what do you have? You have the foci here on this side. This is your center. And it's at 0, 0. Remember, there is no h and k. It's x squared divided by 16 plus y squared divided by 9. So there is no minus h. Okay, so it's at 0, 0. Where is your f? Yeah, it's square root of 7, c, and 0. That's it. Okay, so where is your, let's say, lattice rectum? Remember, this is, f. Let's call this f1. This is f1, l1. Your lattice rectum, f1, l1. Where is l1 at? L1 is the same. L1 is at square root of 7. And remember, when we plug it in the equation of the ellipse as f1, l1 squared, we get b to the power 4 divided by a squared. So if I go and I take the square root of that, I get b2 divided by a. So 9 divided by 4. That's it. Again, and then my directrix, that's the number 1 that I told, number 4 that you need to memorize is a divided by e. What's a? A is 4, and e is square root of 7 divided by 4. So that's 16 divided by square root of 7. That's my directrix on this side. If I want to go to the directrix on the other side, x equal minus 16 divided by square root of 7. And that's how I got all of them by only memorizing 4. Okay? The last one I told you to memorize is this condition. That's the new one. In the beginning, it was only this one. If you want, I said, you can do this, and now the condition, the squared breakfast, the radicalized squared breakfast for the tangent, for any line to be tangent to that ellipse. Exactly, that's it. You know, now, let me see. Do we have time to go to polar? We have to start it anyway. And before we start polar, we're gonna, let me see here, what do we have here? I need to remind you of the polar that we have just studied with the parabola. What did we study with the parabola? We studied with the parabola that, you know, r equal 2p, and then there is an e here, but since it equals 1, get rid of it. 1 minus cosine theta or plus cosine theta if it's opening rightward and leftward, and that's very easy. You can, this is horizontal, that's why it's cosine theta, right? And this one is the minus cosine theta. So we're dealing with this, with opening to the right, with the directrix being here. And then when we, you know, deal with 1 plus cosine theta, we're dealing with opening leftward and the directrix being here. Remember that very well. We studied the parabola because we're going to use that now with the ellipse, even in the polar form. And then we did the parabola opening like this, upward. And then we said this is r equal 2p, and this one is 1 minus sine theta. And in this situation, we're dealing with this directrix here, right? And then this is your f. Now imagine if this parabola now it's open. Imagine if I am to make it an ellipse and I'm going to close this shape. Which foci will that be? Will be the lower one. Yes, exactly. There will be an upper one here. Keep that in mind because we're going to use that. Okay, so this will be my lower foci and this will be my upper foci with relation to the opening of the original parabola. And my directrix will be here. And if it's opening this way, right, my foci will be here, right? And it will be r equal to p 1 plus sine theta, okay? And if I am to close this shape, what happens now to make it an ellipse? This will become my upper foci. Just keep that in mind, okay? We're gonna use all that stuff as we move along with the ellipse, okay? Now, for the ellipse, we can start with something as easy as, you know, this. You already know that. So if we have an ellipse stretching horizontally, and then we take, this is the center, this is F, okay? But now we are in polar. What does that mean? So that's focus at the pole. So that's your new origin. There is no y-axis here. Remember that. So now I have a point P that has an r theta, right? And I have FP, and I have my directrix. Look at that. And then I have my M, and I might have my PF is less than PM. That's why E is between 0 and 1, okay? And yes, I might need to use also this and do some projections. I might call this N. And what do I have here? What's the equation of this x, the directrix? We will find out, okay? Now, the equation of x, the directrix, in what? In the Cartesian world is what? A divided by E, right? But that's from where? That's from here to here. Don't forget that. We're going to use that now. Now, the pole, the origin, the new origin is here. This is your 0, 0, okay? So, x equal plus here, plus A divided by E, that's in the rectangular Cartesian world, okay? Now, if I am to go ahead and say, you know, E equal PF divided by PM. This is how we started for the parabolas, right? What do I get? I got R divided by, what is that? What is that, R divided by PM? What's PM? PM is this WN, right? WN. What's WN? WN is Fn minus R cosine theta. This is your R cosine theta. Okay, so we use that rectangle. So PM is like WN, and WN is Fn minus exactly R cosine theta. Now, what is Fn? Fn minus R cosine theta. Fn, in many books, they call it K. In some books, they call it P. We never want to call it P. We're going to confuse it with a lot of other things. In some books, they call it Q or L. It's the distance between the focus at the pole, the new origin at the pole, the F in, it could be the F on the right side, or the focus on the left side now. Or it could be the lower foci or the upper foci. We're gonna, make sure which foci we are using before we, make the calculation. But for now, I like to call it K. And it's the distance between the focus and the directrix. Not the origin, Cartesian origin, this one, and the directrix. This one, in Cartesian rectangular, x equal plus a divided by e. If I am in polar, what is that x? What is that x? It's just this k, or Fn, okay? So k is this Fn, and I want Wn. So Wn equals k minus this tiny small R cosine theta. This is my R cosine theta. This is my R sine theta, but I don't need the sine here. So I go back here, and all I can say, I can do now E equals R, K minus R cosine theta. And then if I do that, and I do my cross multiplication, I get R 1 plus E cosine theta equals E times K. So R equal E, there is an E here. It's not like the case in the parabola. It's not equal 1. E eccentricity times this K divided by 1 plus E cosine theta. Okay? So now the E is part of that polar equation because it's not equal to 1. And there is a new element. It's called K. K is the distance in the polar grid between the focus, the center at the pole, and the directrix that we are dealing with. Now, this is very important. The directrix could be the one we're dealing with the one on the right, with the one on the left. When we have the ellipse in a vertical direction, we're gonna see which focus and which directrix. Is it the lower foci, the upper foci? Which one we're dealing with? Okay, but the general form is R equal E times K, 1 plus or minus E cosine theta. Now, how do we get to the 1 plus or minus? We get to them by understanding which directrix and which foci we are dealing with, and that's why we're gonna leave that to the next after the break. To the next lesson. I also need a break. I need to drink some water. Okay, so but for now, let's just remember when we're gonna start that there is a new K. K is the distance between the focus, that the foci that is in interest. We're interested in one foci, and many problem now. When you start polar with the ellipse, you're only interested in one foci, and we're gonna link that foci to the parabola. And how is that foci on the side of the parabola that is opening to the right, or opening to the left, or opening downward, or opening upward? Okay, but the general form for a polar equation of an ellipse opening right or left it's not open, it's closed. But look at this here. We're going to talk about this in the next lesson, in the next video. The parabola is opening to the left, right? So if you are dealing with a parabola here, what's the equation? R equal 2p, exactly, 1 plus cosine theta. So if I am to finish this and make it an ellipse and I'm dealing with this, I go with R equal E times K 1 plus cosine E cosine theta. I'm sorry, E cosine theta. Okay, so you just told me we found it out as minus. I started with that to get the idea closer to your mind, but we're going to follow the parabola. And that's why we studied the parabola in the first place. Because an ellipse geometrically is basically you started with one focus point and then you add the other focus point. So in this situation, the general formula, you know, when you're dealing with this focus here, not this one, is it follows the parabola that opens leftward. So it's going to equal EK divided by 1 plus E times cosine theta. Okay, we'll do more of these and we'll do them in leftward, rightward, leftward, opening upward and downward with numbers, with real values. Okay, in the next lesson. Okay, let's go take a break. Thank you guys.